Okay, hello all, thank you for coming. As you may have gathered from the slide, I'm Ben Sachs. My company, Sachs & Associates, does training in C and C++ for companies all over the world. And I'm going to be talking a little bit about freestanding C++ today. But I want to start by taking a little bit of a step back and just asking a question that we don't often ask ourselves, but it's something that I think that sometimes it's helpful to look at this big picture, which is, we have a number of people from the C++ Standards Committee here at the conference, but why do we standardize C++? What benefits do we get out of standardizing the language? And there are lots of different ways that you could answer that question. But I think one of the big ones is that standardization provides portability. And portability has a couple of different aspects. The part we usually think about is the fact that by having standard C++ tools that all work to a common standard, we can write one program and use the same source code, compile it with multiple different tool chains, targeting many different kinds of systems, and have a reasonable expectation that the code, the program that comes out the other side is going to work correctly. But there's another aspect to it, which is that your skills are portable. The things that you learn in the process of writing one C or C++ program can be applied to writing another program, even if the program that you're writing in that second case is targeting a completely different environment, using a completely different tool chain, maybe written for a completely different company. So portability is important, but portability is hard. Standardizing C++ is complicated because C and C++ are used to do so many different kinds of things. We don't just write traditional desktop and server applications in C++. We also write things like operating systems or embedded systems, which some of them have an operating system, others don't. And when you're programming for something like an operating system or an embedded system, you're often dealing with environments where you have to deal with some fairly significant restrictions or limitations. So on some of those platforms, for example, you might not have a file system. Your file system is often one of the features that your operating system provides. If you're in the process of writing the operating system, you obviously can't rely on another operating system to provide file access. That's something you're going to have to write yourself. And so the parts of the standard library that are related to file access, you can't expect them to do what you want in that situation. You might not have certain pieces of hardware, like a real-time clock, in which case the parts of the standard library that give you a real-world time right now might not work correctly. You might not have a dynamic memory pool, depending on what platform you're working on. You might have very limited memory resources, and you don't want to put any of those towards a dynamic memory pool that you could use to allocate objects and then release them whenever you so choose. So these are fairly significant restrictions. These are just some examples. But even for these sorts of applications, you often want to write portable code. There are real benefits that you get out of it. In the case of an operating system, it's just a design requirement in many cases. You want that operating system to be able to run on many different platforms. But even if you're writing code for something like an embedded system, often some of the code that you'll write for an embedded system will be usable on several different generations of the same product, so it might be used on different hardware platforms, or even within the same hardware platform. You might have the situation where I don't want to add another target, but I want to be able to change tool chains easily. I want to upgrade to something that's going to support more modern C++ features. And by writing portable code, that makes that transition easier. Not necessarily free, but easier than it would be if you had a lot of platform-specific stuff in your code. For libraries, if you're a library vendor, and you can write your library in such a way that it's portable to one of these restricted environments, then that increases your potential market. So these are all useful things that you might want to do. But the question is, if you're trying to write code for this sort of restricted environment, I've just given you some examples of parts of the standard library that you can't rely on. So what parts of C and C++ can you rely on in that sort of situation? And the standards answer this by defining two different types of implementations for the language. An implementation is a tool chain that takes in C or C++ source code and outputs an executable program. And so there are hosted implementations and freestanding implementations. And the two standards explain the purpose behind these a little bit differently, but they wind up in more or less the same place. So the rationale for the C standard says, by defining both conforming hosted and conforming freestanding implementations, the standard recognizes the use of C to write such programs as operating systems and ROM-based applications, ROM-based applications being a common way of implementing embedded systems like I was discussing before, as well as more conventional hosted applications. The C++ standard describes it as a freestanding implementation is one in which execution may take place without the benefit of an operating system. So you wind up in fairly similar places because if you're trying to write an operating system or an embedded system that doesn't use an operating system, you obviously don't have the benefits of an operating system. So the hosted implementations are what we would typically use to write a traditional desktop or server application. And this is what we usually think of when we think of C++. It's the full suite of language features and library facilities that are all included in the standard. But there are also these freestanding implementations, and these are what we typically use for writing operating systems or embedded systems. And freestanding implementations are only required to provide limited language and library facilities. So if you want to write C or C++ code that is as portable as possible, that works on the maximum number of C and C++ implementations, it's one of these freestanding implementations that you would be targeting. Those are what establish the lowest common denominator for C and C++. So what does that lowest common denominator look like? So the C11 standard describes it like this. A conforming freestanding implementation shall accept any strictly conforming program, where a strictly conforming program is a program that doesn't rely on compiler-specific extensions or other toolchain-specific features, and doesn't have any platform-specific behaviors that you're relying on. You don't rely on undefined or implementation-defined behavior in the program, in which the uses of the features specified in the library is confined to the contents of the following standard headers. And here's the list of those headers. And what I want you to notice looking at this list is that for the most part, although these are library facilities, they exist by and large to support core language features. So we have things like float.h and limits.h, which provide bounding constants that tell you the size of floats or the maximum value of an integer. We have a number of these headers provide alias macros. So for example, C, unlike C++, didn't originally have a Boolean type built in. So when they went to add one, there were already a number of programs out there in the wild that had defined their own identifier called bool, B-O-O-L. So they didn't want to use that. What they did instead was they made the type that's built into the language called underscore capital B Boolean. And then this header file, std_bool, provides an alias that is BOOL for that. So there are a number of these headers that provide those kinds of alias macros. We also have headers like studdef.h and studint that provide common types like size t or the extended integer types, as well as common constants like null. And then there are a few others that do things like international keyboard support for keyboards that don't necessarily have all of the characters that C was written to expect, as well as studarg, which lets you write functions like printf that take a variable number of arguments. And so what don't you get? Well, most actual functions, pretty much. So for example, you're not required to have any of the headers stdio, stdlib, or string.h. So you might not have input and output functions like fgetC or printf. You might not have the memory management functions, malloc and free. And interestingly enough, you might not even have functions like memcopy and strlen, which are fairly basic functions. I suspect most people in this room, everyone in this room, could write strlen in a matter of minutes. But nonetheless, the language doesn't guarantee it. They really went for, we're going to pare this down as much as possible to just the bare minimum subset of things that we want to be available for C programmers when they defined the freestanding C implementation requirements. So in fact, if you look at it, none of these headers that I listed out define any actual functions. There are some function-like macros in them, but no actual functions. C++ requires a little bit more than freestanding C does. Modern C++ requires most of the same headers, not quite all of them, that C does, as well as these. So we have the atomic header for the atomic template, built-in atomic types, things like that. cstdlib, this is interesting, because cstdlib wasn't required for freestanding C, but now freestanding C++ requires a version of a C header, but it's a special version that only needs to provide these three functions: abort, @exit, and exit. So you might have more than that, but you're only guaranteed in a freestanding C++ implementation to have those three functions in cstdlib. We have the exception header, which defines common exception types, as well as some exception helper functions like getCurrentException and terminate. Initializer list for, well, initializer lists. Limits, which is the C++ version of the numeric limits. New, which defines a bunch of different forms of new and delete. The type traits header for doing type-based metaprogramming, and type info for handling dynamic cast and type ID for working with those constructs. So again, a lot of this exists to provide support for core language features. There isn't a lot in this set that isn't in some way designed to support the core language behaviors of C++. And you also need to be prepared for this idea, as I mentioned with cstdlib, that you might not have a complete version of a header file. Just because you know that a header file exists in a freestanding implementation, the standard does open the door for the idea that you might have a header file that doesn't contain everything that you would normally expect that header file to contain in a hosted version of C++. Now, the library restrictions for freestanding implementations are kind of the most obvious restrictions. They're the ones that people usually think about, but they're not the only ones. There are a few others. So, for example, multi-threading might not be available. Both C and C++ have text in the standard that says that its implementation defined whether a program can have more than one thread of execution in a freestanding implementation. And in practice, many freestanding implementations don't provide the threading libraries for C and C++. Program startup and termination might be different. This one is kind of strange. Most of us are used to working in C and C++ and having a function called main that defines the body of the entire program. The program essentially starts when you enter main. There's a little bit of setup for global variables and things before that, but for the most part, the program starts when you enter main and it terminates when you return from main. And that's not necessarily the case in a freestanding environment. A freestanding environment can define its own name for that function, so it might not be called main, or it might have other behaviors that control program startup and termination. Now, I talked before about C++ requires that abort, @exit, and exit still exist, and those functions are used for doing a certain amount of control. In particular, @exit is used for setting up behaviors to run at program termination. And those functions still have to have a behavior that would be familiar to a programmer who had used them in a hosted implementation. But exactly how they work and what the name of the function that gets terminated when the program ends might be different in a freestanding implementation. Now, aside from that, freestanding implementations of C and C++ provide nearly all the core language features. And in the case of C++ in particular, this includes a number of features that have some fairly significant requirements to them. So floating point arithmetic, float double and long double are all standard types that you can program with without including any headers. And if you're running on a platform that doesn't have floating point hardware, your language implementation is required to provide some sort of software emulation for that floating point capability. You need to have a dynamic memory pool in C++. Unlike freestanding C, where malloc and free weren't guaranteed, new and delete are considered to be core language features in C++. And so some versions of those have to be available, which means you need to have something that looks kind of like a dynamic memory pool, even in a freestanding implementation. Exception handling has to be available. You need to be able to throw and catch exceptions. And runtime type identification. You need to be able to use dynamic cast and type ID in freestanding implementations. Now, a lot of these are features that freestanding programmers of operating systems and embedded systems tend to avoid using. Exception handling and runtime type identification in particular tend to be features that are often avoided in those sorts of applications, some desktop applications too, for that matter, because they introduce a certain amount of overhead into the program, even if the program never throws an exception or does a dynamic cast. So it's not uncommon to see people avoid those features. And in fact, there are compilers like GCC has this fNoExceptions flag that allows you to turn them off. And a lot of people will do that, but it's worth noting that if you use one of those flags, you're actually not really programming in technically C++ anymore at that point. The standard doesn't consider what you're doing to be C++. It's something that looks an awful lot like C++, but it's not quite C++. It's not 100% kosher as far as the standard is concerned. So now, interestingly enough, at the same time, the definition of freestanding hasn't totally kept up with some of the developments in the language. So stood move and stood forward, those functions are defined in the utility header in C++. And they provide important library support for working with R-value references and move semantics. But utility isn't one of the required headers in freestanding C++. It's a header that a lot of freestanding implementations provide, but they're not required to provide it. That's something that they're providing on top of all the things that the standard says they're required to deal with. So you have to be prepared for the possibility that a freestanding implementation might not give you these things. We'll talk about how to deal with that a little bit later in this talk. So if you want to write code that's portable and works well on these sorts of restricted environments, it involves a fair bit of knowledge and attention to detail. Most of the core language features are available, but there are some that you tend to want to avoid in a lot of these applications. And beyond what the library provides to support core language features, you don't get very much of the standard library. Many of the capabilities that we typically think of the standard library as providing aren't guaranteed in freestanding implementations. So if you really want the code that you're writing to be portable to the maximum number of C and C++ systems, you want to restrict yourself both to the library features that are guaranteed in freestanding implementations, as well as the core language features that most freestanding applications actually use. This is particularly true for library vendors. Now, many freestanding toolchains actually do provide more of the standard library than they're required to. But you have to be a little bit careful about using them, because one freestanding toolchain might provide 60% of the standard library, and another might provide only 30%, and it might not be overlapping segments. One might provide some functions and one might provide others. And so using parts of the standard library that aren't guaranteed in freestanding can wind up making your code less portable than you'd thought. And unfortunately, there aren't a lot of tools that exist for helping you know when you've strayed beyond the boundaries of what is required for freestanding C and C++. So you kind of have to be aware of these limitations and know how to police yourself in terms to make sure that your program is as portable as you intended it to be when you're targeting a freestanding implementation. So I'm changing gears here for just a moment. Some compilers have a flag that looks like this. -f freestanding is what GCC calls it, but there are other compilers that call it other things. Now, GCC, many distributions of GCC, provide a full hosted implementation of C++. So if they were already going to do the work of providing a hosted implementation, what's the point of including this flag? What does that -f freestanding flag actually do? What it turns out it does is modern compilers don't necessarily just treat the standard library as an opaque black box. They have a certain amount of knowledge about what certain functions from the standard library actually do. And they can use that knowledge to generate more optimized code in some circumstances. So, for example, if I wrote code that looks like this, size t n equals strlen of hello, and I feed this to GCC, GCC has some built-in information about what the strlen function does. And so the code that comes out the other end doesn't actually include a call to a strlen function from the library. It can see the string hello, it knows the length of that string at compile time, and it will generate code that looks as if I had just written size tn equals 5. It doesn't actually need to generate a call to strlen. Now, it can only do that as long as it can see the length of the string. If I'm dealing with a situation like this, where the length of the string is unknown because it's a function parameter or something else, in that case, GCC has to actually generate a call to the strlen function. So there are some circumstances where this knowledge is helpful to the compiler, allows it to make certain optimizations, and other places where it's thanks for sharing, but I can't actually do very much with that information at this point. So what the -f freestanding flag does is it turns off a lot of that built-in knowledge. The description of the flag says GCC does not make assumptions about the meanings of function names from the standard library, with exceptions noted below, and we'll talk about those exceptions in just a moment. So why do they do this? Think about how a freestanding implementation might work. If you have only limited library facilities, I mentioned before that strlen isn't a required function in a freestanding implementation. So some distributions of GCC might not have a version of the strlen function included with them. But those versions of GCC might still have this built-in knowledge enabled. And in that situation, in some places I could write a call to strlen, and the compiler would be able to take advantage of its built-in knowledge and avoid actually generating a call to strlen. And my code would appear to work fine, even though my library doesn't include a strlen function. And then in other places, I might try and write a call to the strlen function. And in that case, the compiler would have to actually generate a call to the function, and I'd get a strange link time error that says strlen doesn't exist. And I, as the programmer, would be very confused because I'd be looking at this code and I'd say, but it worked over here. What the heck is going on? And that could take quite a while to resolve. That could be a very difficult bug to figure out. So turning off this built-in knowledge means that all of the calls to strlen will be treated equally. And if the function isn't there, it won't work anywhere. And that creates a much easier situation for programmers to understand. Yes? Mm-hmm. No. The compiler would, oh, sorry. Can you, there's a microphone here. Can you come up to speak the question for the tape? No, the compiler will not complain in that situation. In that situation, every call to strlen would actually wind up generating, the compiler would generate code that would actually call the underlying strlen function. And if the library provides the strlen function, that's fine. It's only the situation where if you don't have a strlen function, and some of those calls would succeed, but would appear to succeed anyway, because if the freestanding flag wasn't provided, the compiler would assume certain behaviors about strlen, and it might not actually generate a call to the function. In that situation, certain calls could look like they succeed because they don't actually call the strlen function at all. They don't need it to be there. Other calls would need the strlen function to be there, and they would find out it doesn't exist. And that's when the compiler would complain. If the function actually exists, you wouldn't get any complaints, regardless. Does that answer your question? Mm-hmm. 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 Right. So if you specify if you don't specify the -f freestanding flag, and you have an implementation of strlen, doesn't matter, everything will compile, because you'll either call the strlen function, or the compiler will use its built-in logic to do something equivalent. If you don't use the flag and you don't have a strlen function, then you can be in a bad situation because some calls would appear to work because the compiler wouldn't actually generate a call to strlen. It would use its own internal logic to do the same behavior. Other calls would fail because they would be trying to call a function that doesn't exist. If you use the flag and you have the function, every time you tried to call the function, it would actually call the function, the underlying function, and it would work everywhere. If you use the flag and you don't have the function, it will fail everywhere because every call to strlen would generate a call to an underlying function that doesn't exist. And then so you would get a consistent behavior either way.
So to summarize, this flag helps to identify inconsistent behavior between compile time strlen and link time strlen.
Yes, it
Okay,
prevents you
thank you.
from seeing a mismatch there.
Okay, thank you.
Yeah. So the exception I mentioned, this is specific to GCC. The functions memcopy, memmove, memset, and memcomp are all, a certain amount of knowledge about those functions is built into GCC at a deeper level, and that's present even if the -f freestanding flag is there. And those functions are actually required to be there in GCC. Even if you have a freestanding library distribution, GCC says those functions have to be there, and if they weren't included with your library, you have to write them yourself so that I can work correctly. Now, there's another use that people have come up with for this -f freestanding flag, which is that in some cases, you want to use a different distribution of the standard library than the one that's usually packaged with your compiler. That is, you still want to use a version of the standard library, but you want one that's designed with a different implementation on the back end, something that might have slightly different performance characteristics or size requirements, something like that. And in that situation, using the -f freestanding flag can also be important because there's a slim chance in that situation where if the compiler makes assumptions about what a standard library function does, how it's implemented, and those assumptions don't hold for whatever version of the standard library you're substituting in place of what the compiler was expecting to use, then you could get strange behavior in that case. It's not very likely. Most of the standard library functions that we're talking about have fairly simple behaviors. But to be on the safe side, it's something that people often recommend that you do if you're going to substitute a different standard library definition for the one that your compiler might have assumed that you would be using. That said, that can be a little complicated because the dividing line between the core language and the library is somewhat blurry. We've already seen some cases where there are parts of the standard library that exist to provide library support for language features. But there are also parts of the standard library that require a certain amount of support from the compiler. So earlier I mentioned the type traits header that lets you do compile time programming and ask questions about the nature of types at compile time, which can be very useful for certain types of template programming. So you can use these type traits like is integral of t. You can put in whatever type you put in place of t there. Is integral of t : value will be true if t is an integral type like int or unsigned or something like that, and false if it's a floating point type like double, or if it's a class type that doesn't have a numeric meaning, things like that. Is abstract lets you ask whether something is an abstract base class. Is volatile lets you ask whether a type includes the volatile qualifier. And there are a whole bunch of these different type traits defined in that type traits header file. Header, I should say. So Some of these type traits can be implemented in standard C++. Is volatile, for example, isn't too hard to do if you're familiar with how to write template deduction guidelines and things like that. On the other hand, is abstract really requires a certain amount of support from the compiler. It's difficult to write code in C++ that will determine whether something is an abstract base class or not, and will still compile if the answer turns out to be no. And this sort of interaction can make it a little bit complicated to substitute a different standard library distribution for the one that comes with your compiler. It's still something that people do regularly, but it does have these few corner cases where you might get some complexities. So we've looked at some of the difficulties that you might have in trying to write code that is designed to be portable to freestanding environments, because you need to stay away from both the library features that you're not guaranteed to have in a freestanding environment, and also the core language features that freestanding environments tend to avoid. Now, there is work being done on the standards committee to try and simplify this picture a little bit and make your lives a little bit easier if you were trying to do that. And so there are proposals that would involve making certain core language features optional, as well as guaranteeing more portions of the standard library in freestanding implementations. So one of these papers is Leaving No Room for a Lower Level Language by a fellow named Ben Craig and myself. And it proposes making certain core language and library features optional in freestanding environments. So the default implementations of new and delete, new and delete would still exist for the purposes of providing your own implementations, but the library would no longer be required to provide its own built-in implementation of new and delete. Exception handling, the abort, at exit, and exit functions, floating point arithmetic, multi-threading, and lock-based atomics. Some atomics use locking internally, others are natively atomic on your platform. The native atomics would still be guaranteed, but the lock-based ones would not be. Runtime type identification and thread-safe static initialization. Now that C and C++ are thread-aware, local static objects have to include a certain amount of behavior to make sure that they're never initialized more than once if you happen to enter the function in which they're defined from multiple threads simultaneously. And so many of these are features that freestanding environments already tend to avoid. Others, like multi-threading, are commonly used, but not the standard library version of multi-threading. The standard library's implementation of threading really expects support from an operating system. So it's not what you tend to use in freestanding environments, even if you are trying to write multi-threaded code. Now, there are other parts of the standard library, though, that don't use very many of these features. Many of the STL algorithms, like find or sort, don't require the ability to throw exceptions or do runtime type identification, for example. There are others that use them, but only in small ways that can generally be avoided. So, for example, the std_array class does have a member function that throws an exception, the @member function. It throws an exception if you try to access an element out of bounds. But std_array is still perfectly usable without ever calling the function. There would be a lot of use that you could get out of it in a freestanding environment, and you would just stay away from that one function if you were operating in an environment that didn't support exception handling. So Ben Craig has other papers that would aim to guarantee that more of the standard library would be available to freestanding implementations. And in the case of things like std_array, what you would get would be a partial version of the class in some cases. So some member functions would be guaranteed, others would not be guaranteed in a freestanding implementation. And this is sort of similar to how I already mentioned that cstd_lib, the version that you get in a freestanding implementation, might not be a complete implementation that you would expect from a hosted version of the library. Now, so if these papers are adopted, they could simplify the process of writing freestanding applications, but there are still some lingering questions. So, for example, one of the concerns that we've run into is that guaranteeing more of the standard library is available in freestanding implementations would make it harder to substitute a different library distribution for the one that comes with your compiler. It's not clear to me that that has to be the case. If you still want to use a standard library distribution, you would just have to use whatever you're substituting in place of the library that came with your compiler would just have to also include all of the new things that would now be required of freestanding. But there are some concerns about that. There's also the issue of organizing the standard library into modules. So modules are coming in C++20, but the C++20 standard doesn't do much in the way of reorganizing the standard library into modules. But there is interest on the standards committee in doing that kind of reorganization at some point in the future, possibly C++23. And if that reorganization happens, how you draw the lines between the freestanding parts of the freestanding modules and the hosted only modules is a complex question that we'll need to solve. But, so, if you are interested in helping out with that, by all means, let me know. In the meantime, what can you do to make it easier for yourselves to write freestanding code? It depends a little bit on what sort of project you're working on. So if you're an application developer, generally speaking, you have...
Yeah,
yes?
Question. Have you mentioned the paper number?
The paper number for leaving no room for a lower level language is P1105, I believe. The others, the library paper is a whole series of papers with numbers. I believe it's 1366 and 1367 at the moment, with the intent of adding more on at some point in the future. But I'd have to go back and check to make sure about those numbers. So anyway, if you are an application developer, you generally have some knowledge about what platforms you're deploying to. And you can use that knowledge to make informed decisions about what parts of what core language features are likely to be suitable for the applications that you're trying to write. So for example, you might know as an application developer that you're always going to be targeting hardware that has floating point support built in. In that situation, using floating point operations isn't so bad because you can be fairly confident that there's going to be a pretty low overhead introduced as a result of using floating point operations. The hardware will take care of most of that for you. So you can make these sorts of informed decisions as an application developer. For the library parts, there are a lot of parts of the C and C++ standard libraries that can be implemented in standard C and C++. So for example, here's an implementation of memcopy. It's a fairly simple function. You can even do this for functions like std_move, which it's not a simple function to write. You need to know a fair number of language features in order to write this sort of function. But it is something that can be written in standard C++, even though it's the sort of thing where as a language support for a core language feature, or as library support for a core language feature, you might expect that it would be in some way built into the compiler, but it's not. And both of these implementations were things I found with just a simple Google search. Now, I realize that doesn't sound very helpful just yet because, well, I don't want to have to write the standard library myself. That's not very helpful. I can write my own code. The point of having a standard library is usually so that I don't have to write all of that code every time. I'm not really suggesting that you write these in every case. What I'm suggesting is the fact that because you have the option of writing them, because they could be written in C or C++, what you can do is you can wrap up the portions of the standard library that you need inside your own namespace using things like using declarations, like this. And then all the rest of your code, in this case, I'm using namespace Ben, all the rest of my code would refer to Ben : memcopy, not stud : memcopy. But I didn't have to write memcopy myself. I just borrowed the standard library implementation. If I ever happen to find that I'm trying to compile my code on a platform that doesn't provide me with a copy of memcopy, then I can go ahead and implement it. But in a lot of cases, I'll never need to, because a lot of freestanding implementations will provide many of these functions like memcopy. So I can leverage the standard library, but through the use of my own namespace like this, I can provide a layer of abstraction that means that if I should ever have to write it myself, I have the option of doing so. Now, what if I have to support multiple different tool chains, and each one of those tool chains provides different parts of the standard library? Something that can help out a bit with that is the inline namespaces feature. So it looks like this. You'd write one header file. It would have your namespace, Ben, or whatever you choose to call it in your case. And then inside that namespace, you would have a bunch of individual namespaces for each of the platforms that you intend to support. And within those namespaces, you would either use the standard library implementations of the functions you needed, or you would bring in your own implementations for the platforms that don't provide some of those functions. And then you would conditionally compile one of those namespaces as an inline namespace. And when you use an inline namespace, all of the members of an inline namespace become members of the enclosing namespace as well. So whichever one of these is compiled as the inline namespace, all of the names in that namespace become members of namespace Ben, and I can just use them directly. And this makes it a little bit easier to manage the collection of functions that I'm borrowing from the standard library. It's easier, if it's all in one header file, I can easily see that I went through and added the function to all of these different versions. Whereas if they're in separate header files, it would be easy to miss one, and then someday in the future I try and compile for a particular platform and I find out that some of my functions are missing. That's not very helpful. Now, as a library developer, the problem that you're faced with is a little bit more difficult because you need to be prepared for the possibility that your library could be used on any platform, essentially. So there you really do need to be restricting yourself to the freestanding only portions of the library and freestanding only features. So you want to clearly document as a library author which language features from this set your library uses so that freestanding users can make an informed decision about whether they want to use your library. They can tell at a glance, oh, this thing uses floating point arithmetic, but that's fine because I have floating point hardware. Oh, but it also uses runtime type identification. I don't really want to pay the overhead for that. Maybe I shouldn't be using this library. Now, you also have to really stick to the freestanding only, the required freestanding portions of the standard library. You can't really pull the same trick that I showed for application developers where you borrow pieces of the standard library because your library might be used on platforms that haven't been created yet. it might be using a tool chain that doesn't exist at this point. So even if you knew for a fact that every existing freestanding implementation of C++ actually provides stood move, you wouldn't really want to use it. Or the safest thing to do would be to write it yourself, because someday in the future, because it's not a required part of the freestanding set of language features, there could be a tool chain that doesn't provide it. So the safest thing to do in that situation is write the pieces of the library that you need yourself. That brings me to the end of the talk. I'm happy to take some questions, but otherwise I hope you find it helpful. Thank you for coming.
Hello, Software Talk. Just have a question. If I use memcpi and all these functions in freestanding mode, do I lose the optimization the compiler usually does? For instance, I do memcpi of 8 bytes, it will end up only in a move instruction, for instance. And do I lose that because the compiler removes the semantic that you usually knows?
I'm sorry, can you, I didn't quite catch some of that. Can you, I was getting some feedback from the microphone, so if you could.
Sorry.
Yeah.
If I just do memcpi of 8 bytes, for instance, in hosted normal mode, usually the compiler optimizes it in a single move instruction, for instance. Do I lose that if I use freestanding mode because the compiler loses the semantic of these functions?
Yeah, if you're using the -f freestanding flag, in that case, I mean, it would be up to the behavior of the compiler. So I believe in the case of GCC, you would still get that behavior because memcopy in particular has a special behavior even in freestanding mode for GCC. Other tool chains might work differently.
But it's okay, but it's GCC specific. It's not something.
Yeah, but in GCC, it's expected that memcopy will be there and that the compiler can rely on it having the normal semantics.
Oh yeah.
Even if you get a different behavior. So the compiler will generate special code in certain memcopy situations.
Oh yeah.
Even in freestanding mode.
Oh yeah. Thanks.
There's a lot of work being done to allow constexpr in many more situations, specifically with like containers.
Yes.
That seems like something that would possibly be allowed with a freestanding environment, even if that container could not be used at runtime. And I see some parallels with like built-in knowledge about these functions, things that the compiler knows at compile time but doesn't know at runtime. Is that a possibility that those constexpr-aware containers are going to be available in the freestanding environment?
I think it's possible. I mean, I think that that's something that could be added in a library proposal. I don't know of a portion of the papers that I'm familiar with from Ben Craig that actually call for the sort of situation where, so at the moment, usually constexpr on functions means maybe constexpr, right? A constexpr function can be called either at compile time or at runtime. But there are also interest in functions that can only be called at compile time. I think if you have a version of the behavior that can only be used at compile time, if we have language support for that, then you could theoretically specify that the freestanding implementation has to provide the compile time constexpr versions of certain features, but doesn't necessarily have to provide versions of them that can be used at runtime. So you might have instead of a constexpr function, the freestanding version might be a constexpr bang function. I've usually seen it written as a constexpr with an exclamation point for must be run at compile time. And I think that could be possible. I don't know of work that's currently being done in that to guarantee that, but it's certainly a direction that we could pursue.
Thank you.
Just a quick follow-up to that. So I think it's with C++17 where you can make const expra variables.
Yes. Well, I think you could make them before C++17, but you definitely can make them in C.
Oh, template variables. You can make template variables. I guess that's what it was.
Yes.
But I guess the question would be, is there any way that you could either use a const expra declaration of a global instance of one of these containers, and then you wouldn't need const expra bang because it's guaranteed to always be const expra if it's not a function? I guess then the question is, how would the member functions of this const expra container work in that context?
Okay, yeah, what I was thinking was, yes, you could have a const expr variable of that sort of container type would be able to exist. The compiler would be able, I would imagine that the compiler would be able to determine that that has to be done at compile time. What I was thinking would have to be const expr bang was the constructor on, if you want to be able to have a vector that is constructed at compile time, but your library doesn't want to provide a vector that can be used at runtime, the constructor of vector might have to be declared const expr bang. So that was what I had in mind, but I haven't given it a lot of thought. It's, I think it's a possibility.
So would you say that this can be a technique to deploy applications even on desktop without having to worry about dependencies, for example? Let's say I want to write a command line utility and I want to be able to ship it to multiple people that I just don't know what they're going to be running or what kind of libstandard C++ they're going to have, what version. Can I just build it as freestanding and then give them that standalone binary, if you will?
Well, I don't think you can give them the, if you want it to run on multiple platforms, they're going to need a binary specific for each platform.
No,
That's still
let's
going.
assume Linux, for example. I'm targeting Linux, and I want to give them a binary that runs on Linux, without having to worry about like what version of glibc or libstandard C++. If I build my application with -f freestanding, would that give me a standalone binary that basically runs on its own, or that's not possible?
I'm thinking. Normally when I write this sort of thing, I'm used to the functions being compiled in, so so you wouldn't necessarily need to use the freestanding mode to ensure that the program would run everywhere. If you're using a DLL system or something like that to link in those functions, I suppose that this could provide you with a certain amount of protection in that case. But it's tricky because you still do have to sort of police yourself in that the freestanding mode of the compiler would just guarantee that the functions are called. It doesn't guarantee that you're only using the freestanding portions of the library. So I think if what you're interested in is, I don't want to have external dependencies on libraries that could be different on different platforms, you would need to, the safest thing to do is to just not call those functions, essentially. And whether the freestanding flag on your compiler helps with that is going to depend on your specific tool chain, whether that changes which portions of the library are available or not.
Okay.
Does that, yeah.
There is some work in Snapshot to package up DLL and remove platforms, even if DLL
Yeah.
is kind of
Do you want to use the microphone so that you can? Yeah. Yes, I'm going to make you walk over there. Yeah.
I was just going to say that just some work on Snap and Flatpaks that will do some of that packaging of the DLLs, so you don't have to worry about dependency problems. I know it's a pretty big thing in Ubuntu and Fedora. But then you could also always just compile as static pi, which is another thing that GCC and Clang are working on. That would take all the functions you care about and compile it all into one executable, and then you can move it anywhere.
Okay.
thank you for this really nice talk. I enjoyed it very much. Just these few questions kind of got me thinking. I remember that with one compiler I was working on, the system didn't support floating point types, but if you have expression that is consistent only from floating point literals, you could use that. So you had like a compile time support without runtime support. So there were questions regarding the libraries, containers that can only be supported in compile time and not in runtime. And also one thing that comes into mind is this const eval keyword, new for C20. So maybe if you can get your opinion of that, if all those things can come together maybe in some future.
Yeah, there are certainly some possibilities there. I'm not quite sure if were you just saying, I think this is a possibility, or was there a question that you were hoping?
Yeah, well, just your opinion of that, because somehow, I thought about all those things, and I was wondering, what do you think about it, and whether it's some way to go forward with freestanding C++?
Yeah, it really depends. I mean, there are certain environments already that call themselves C++, but don't necessarily provide all of the behaviors that you would typically associate with C++. So there are already all of the things that I listed out where, such as default implementations of new and delete, there are already platforms that give you most of C++, but aren't really technically standards compliant because they don't actually give you a default implementation of those things. And so the papers, one of the papers that I mentioned is trying to give you the option of not providing those things. But I think that, as we move into more and more compile time programming, this picture does get a little complicated in terms of it does make sense in some respects to be able to use the front end portion of the compiler to do certain behaviors that maybe you don't want to be able to do at runtime. Now, I'm not sure exactly how much utility there is there, because I'm trying to think of what sort of program would use floating point only ever at compile time and never need a floating point value at runtime. But yeah, there are certainly some possibilities there. I think we're out of time, so thank you all for coming once again, and enjoy the rest of the conference.